Hi everyone, welcome to this M2D2 meeting today. We'll be talking about 3D reaction prediction with Pierre van Gerwen. I hope I'm not mispronouncing that. Pierre is a final year PhD student at the laboratory of Clemence Comenberth at EPFL. Her research focused on the interplay of chemical and physical based prior in machine learning models for molecular and chemical reactions. Thank you so much, Rick, for accepting our invitation to present your work here today and looking forward to it.
Thank you very much for hosting me today. So I'm happy to be sharing some recent work. So I'll be talking indeed about geometric deep learning for chemical reactions. And so just to kind of introduce chemical reactions for those who are not familiar, they're typically represented with these kinds of two-dimensional drawings where each molecule here is represented like in a plane. And also it's very common in chemistry, just for the notation, that you don't indicate atoms when they're implicit. So here, for example, this is like a carbon-carbon double bond. This is a carbon-carbon single bond. And then when there are other elements, they're kind of explicitly given. But so this is kind of an example chemical reaction given in a standard format. So you can already see that you can think of the molecules in a reaction as graphs. And you could also think of molecules in a reaction as a string. So in this case, for example, you're representing the same reaction, but now you have the reactants separated with a dot, and you have reactants and products separated with this double-headed arrow. So both are valid, let's say, representations of chemical reactions. And I will talk about a slightly different way to describe chemical reactions. So this is kind of the computational chemistry way, or a quantum chemistry way. And these kinds of diagrams are called reaction profiles. And this illustrates the same information with a little bit additional information, let's say. So here you have the same reactants now given in three-dimensional coordinates. So they're no longer in a plane. They also have like a third dimension. And similarly, the products. But now we also have an additional quantity, which is called the transition state. So if you imagine this diagram describing how the energy of the molecules is changing over time, then in order to pass from reactants which are stable and products which are stable, you have to pass through this short-lived, unstable structure, which in terms of the potential energy profile is a first-order saddle point. And this is called a transition state. And this quantity, or this structure, leads to an important quantity, which is the energy barrier. So in a quantum chemical description of a reaction, you have these two quantities. You have this reaction energy, which basically tells you whether your reaction is thermodynamically feasible. And you also have the barrier, which tells you whether it's kinetically feasible. And so both are important to determine whether a reaction will proceed. But the latter quantity, so the barrier, is much more challenging to predict from a machine learning point of view, because you basically want to make these predictions without using the transition state geometry. So the transition state geometry estimation is the most challenging step when you basically want to do like a quantum chemical analysis of this reaction. Even obtaining, let's say, a guess of this structure is very challenging. So in principle, you want to predict this barrier without any information about the transition state geometry at all. And this has kind of led to two different approaches. The first is to actually try to predict this transition state structure directly. And I add this kind of like quantum chemical notation for the steps that you would need afterwards to get the barrier. So this quantity, because it's an energy, you would first need to, if you had an estimate of the geometry, you would first need to optimize this geometry, and then you would need to do what's called a single point to get the energy. And then you could get the barrier, or you could instead predict the barrier directly. So I will be talking about direct barrier prediction, but there's also a lot of work on the geometry prediction, and they're both kind of trying to solve the same problem. So in terms of machine learning activation barriers, maybe the most common approach is the following. So in quantum chemistry, we also have what are called levels of theory. So this is basically how expensive is my computation, and typically, how expensive is how accurate. And there are some cheaper methods which do lead to some quite reliable results. So quite a common approach is to go for a cheap estimate of the geometry. So actually still using the geometry information, but in a cheap way, and then computing descriptors based on that geometry to kind of featureize the machine learning model. And another approach, which I will talk about in more detail, is a condensed graph of reactions. So this is kind of a 2D description of a chemical reaction, which I will talk about in more detail. You could also directly use the reaction smile strings that we saw and feed them into transformer models or into other types of fingerprints. And you could also use the 3D geometries of reactants and products, and I will call these kind of physics-inspired fingerprints, and I will also talk about those in more detail. And if you're interested in how these different models compare, I did do a thorough benchmarking study to see what are the relative merits of these different approaches. But I'll be talking only about the, let's say, the physics-based way, and I'll be talking about some benchmarks that we can compare to. So talking more about this condensed graph of reaction, or this Chemprop model, this will be one of the baselines that we use for comparison for our own model. And the idea behind it is relatively simple. It's basically saying there are already pretty good like message passing neural networks, for example, for molecules. So all we need to do to use them for reactions is to define a graph for a reaction. And this is not necessarily so easy because typically, let's say this is a molecule. It's very straightforward to understand what should be the nodes and what should be the edges. But now if you have a reaction, it's more challenging to define what should be the node and edge features. So if here, for example, you have a reaction where you had 3 atoms connected in a chain, and then you just broke the bond between atoms 1 and 2, you could represent this in a graph by, first of all, basically illustrating that this bond between 1 and 2 is broken. So you can do this by concatenating some original features from the reactants and basically concatenating some empty features to say this bond was broken. And then for each of the atoms, you are taking the same atom that is present in the reactants and in the products, and again, kind of concatenating their features in the reactant state and in the product state. So this is quite a natural way to define a graph for a reaction, but the problem is that it does depend on what is called atom mapping. So this is basically this information that you know that atom 1 is still atom 1 in the reactants and in the products. And in most realistic examples, this is much more challenging. So here, for example, you have a bigger molecule where you would need to know where every single one of these atoms was present in the products and also in the reactants. So as you can imagine, this basically either requires you to have a chemist that is able to kind of identify the transformation rule that is taking place here and to do this annotation. So this is what I will call true atom mapping. So this is either done by a chemist, let's say, or by using the reaction mechanism. So you can also extract this kind of information, again, by using the transition state. And you can also use open source automated tools. So the best tool that is currently available is Reaction Mapper. So this is trained in an unsupervised way, and it does have quite good performance, but because it's trained on patent data of certain types of reactions, it will not work all of the time for, like, let's say, every type of chemistry. And as I will also show you, you do kind of see a little bit of performance loss when you move from like real atom maps to atom maps deduced by a machine learning tool. And then to talk a little bit about these molecular or physics-inspired fingerprints, I will first talk about molecular fingerprints, and then I will talk about reaction fingerprints. So many of you might have heard of this Coulomb matrix. So this is kind of the like stereotypical example of how you can define features in a like a physics-based way. So here, for example, if you have a matrix which represents all of the atoms in the molecule, and again, all of the atoms of the molecule, you can represent an interaction term between these atoms using a Coulomb potential. And so this is like a physical law that describes how two particles interact. And this can be used to construct a representation if, for example, you just keep like the lower diagonal of this matrix. So this was introduced now like more than 10 years ago, and other variations have emerged, which are kind of, variations on the same theme. But for example, this featurization called SLATM just takes not only a two-body interaction, so an interaction between two particles, but also between three particles. And these are, again, like physically inspired interaction terms, and these can be used to construct features. So these are interesting because they are naturally SE3 invariant. So I will talk a little bit more about what that means. They're physically motivated, and they're robust. They've been demonstrated for many quantum chemical properties. So these will kind of inspire the model that I'm talking about today. But these are now for featurizing molecules, and we need to featurize reactions. So the kind of natural extension to featurize reactions is to construct these fingerprints for each of the molecules that's present in the reaction, and then construct a reaction fingerprint by linearly interpolating between these structures. So just taking the difference between the products and the reactants. So this is something that we have done. And we've also introduced other variations of similar concepts, which are more compact, because having these kind of higher order interaction terms does lead to like an exponential growth of the size of your features. So again, because these are based on molecular representations that have certain properties, the reaction variations also inherit these nice properties. So just to go into some more detail as to why these properties are important, if we look at a molecule here, I can look at some of its properties. So I might want to look at a scalar quantity, which is the energy, and I also might want to look at a vectorial quantity, which in this case is the dipole moment. And I'm interested in how those properties change when I perform certain operations. So if I were to translate this, rotate this molecule, you can see that the energy stays the same, but the dipole moment, the direction changes because it's a vector. And so we can summarize this by saying that under rotation, the energy is an invariant quantity, but the dipole moment is an equivariant quantity. And if I were to instead translate my molecule, this would keep the energy the same, and it would also keep the dipole moment the same. So in this case, both quantities are invariant under translation. And if I were to invert my molecule now, I would again flip the sign of this dipole moment. And so we can see that under inversion, the scalar quantity is invariant, but this vectorial quantity is equivariant. And there's a whole mathematics that describes this kind of behavior. So this kind of rotation behavior is summarized by this SO3 group. The translation behavior on top of that gives us the SE3 group, and also including inversion gives us the E3 group. So these are kind of the natural symmetries of molecules that we really want to be able to encode. And so if we wanted to do this, for example, in a neural network, where we, let's say, transform some features with some weights, an equivariant operation would basically mean that it wouldn't matter whether we perform the group action, such as a rotation, on the initial features or on the output of the function. So we can also say that this commutes with the group action. If instead it was an equivariant operation, it would behave like the identity because it has no effect on the property. So this is the kind of symmetry that we want to be able to encode. And in terms of how we could actually do that in an invariant implementation, for example, we could take this molecule and if we wanted to describe this atom, for example, we could look at some of its neighbors and use distances to those neighbors. We could also use angular information. So this is very similar to like these physics-based featureizations that I mentioned. And this is quite simple because all of the features are scalar. So this is nice and convenient. And if we instead wanted to featureize a molecule in an equivariant way, this is more complicated because we want to basically use a mixture of scalar and vector and maybe some other higher order tensorial features. So here, for example, rather than just using a distance, we might want to use the actual distance vector. And we might also want to use some vectorial information in the node features, for example. We might want to not only encode the atom type, but also encode the actual positions. So it is actually much more complicated to encode these kind of mixed types. And this is done most frequently by, I will be talking about how it's done in this Python package E3NN, which is summarized in reference 2. But this is quite a common way to think about doing it. Basically, you can categorize your different types of tensors, so your scalars, your vectors, and your higher order tensors, according to how they behave under rotation and inversion, which is described by parity. So I won't talk about translation, because translation is actually quite easy to encode, because here, for example, as soon as you use internal distances, it doesn't matter if you translate your molecule. But so the challenge is in describing the rotation and the inversion. And it's very convenient to do this with spherical harmonics. So these are functions which have the same transformation behavior as what are called irreducible representations, which is what we'll want to be using to do all of our featurization. And here, for example, the L equals 0 spherical harmonics, they're spherical, and so they are our first order, and they're also even under inversion. So this is kind of what is labeled with this 0e. And then the L equals 1 spherical harmonics, these now have 3 degrees of freedom, and they are also odd under inversions. This is what is labeled with this 1O. And the L equals 2 spherical harmonics, now they have 5 degrees of freedom, and they are again even under inversion. So together, these three types of functions are typically enough to encode all of the symmetry that we might want to describe, but you can actually also use higher order spherical harmonics if needed. So I will also be talking about the tensor field network type architecture, which is in reference 3, but there are also other ways to do this. But in the tensor field network architecture, the key is to use continuous point convolutions now, which basically have a radial component, which just takes the distance quantity, so just the scalar quantity, and then all of the more complex behaviors, all of the equivariance behavior will basically be encoded using the spherical harmonics. And also most of the learnable parameters are in the radial part. And what's also challenging, not only do you need to initially encode your features in an equivariant way, but you also need to propagate this equivariance through the network. So this is typically done or naturally done with geometric tensor products. So here, for example, if you wanted to take some outer product between two three-dimensional vectors, you would end up with a 3x3 matrix. And this is the outer product, or the geometric tensor product. And this naturally decomposes into 3 components. So the first component is a scalar quantity, which comes from the trace of the matrix. And this describes these invariant or L equals 0 terms. And then you have the antisymmetric components, which actually correspond to cross product. And these correspond to L equals 1 terms. And then finally, you have this symmetric traceless component, which has 5 degrees of freedom and describes the L equals 2 terms. So these are kind of the tricks that are used in the implementation of E3NN. So this is not something I have implemented myself, but this is kind of the keys to understanding how equivariance might be implemented for molecules. So now taking this in, or keeping this in mind, we can think about how to featureize reactants and products in a symmetry adapted way. So if we feed each of our individual molecules through these symmetry adapted equivariant channels, we can end up with representations per molecule that have encoded all of the relevant symmetries. But now the challenge in a reaction context is how to combine these representations, because these individual channels, this is now quite easy to implement with existing tools. So how to do this combination in the best possible way for chemical reactions. And yeah, as I mentioned, these are already implemented. And it's also actually worth mentioning that it's very easy to switch the networks to being invariant rather than equivariant by just fixing the spherical harmonics you use to only be the scalar ones. So this is a nice way to like automatically flip between invariant and equivariant. But so now how to combine these representations for chemical reactions. So if I first focus on the bottom left figure, this is the most similar approach to what I showed you earlier for how to combine these fingerprints, physics-based fingerprints for chemical reactions. So here, if I have these individual channels and I learn like a per molecule representation, all I need to do is add some kind of pooling layer, which gives me then a per reaction representation and can make predictions. But I might also want to encode some additional information. So I mentioned that sometimes you have atom mapping. And if I want to encode this atom mapping in my network, this basically means that I need to permute the order of the atoms in the reactant or in the product to make sure that if I were, for example, to do a difference between reactants and products, I want the difference to be between atom 1 in reactant 1 and atom 1 in reactant 2. So I really want, or in product 1, sorry. So I really want to make sure that the correct atoms are compared if I have this mapping information. And you can also have an attention-based surrogate for the mapping information, which also kind of tries to learn this atom-to-atom map. So in this case, we now have a per atom representation of the reaction, which can then be used to get a reaction representation and then make predictions. So this is what I call the vector mode, because you still end up with like one vector per reaction. And then we also look at the energy mode. So in the energy mode, if again, you focus first on the lower figure, in the case if I had no atom mapping, what this would mean is that I actually want to learn an energy contribution per molecule. So this is actually simpler than the vector mode, because I'm running almost independent channels, because I learn an energy contribution and then I have some kind of like difference or sum or some kind of linear operation or an MLP to predict the final energy. So I wouldn't expect this to work in most cases, but we do find that it works in some cases to basically have this energy contribution instead. And again, you can adapt this to also use atom mapping information to basically, again, make sure that you have atoms in the correct order before you get the per vector representation. I just see that there is a raised hand.
Yeah, hi. Sorry,
Hello.
so I might be misunderstanding this, but so you're featurizing both the reactants and the products as the input on like the top left vector mode.
Mm-hmm.
So does the data come in such a way that like the geometries are positioned relative to each other? Like
no, so typically they are in individual, like the geometries are not related to one another. You can have a situation where you have what is called a complex, in which case you do have the geometries relative to each other. But in that case, rather than treating them as individual components, you would actually treat them as like a single reactant, because the distances between the reactants in that case would already be contained in that data format, and so you wouldn't want to separate them. But typically they're separated, and so yeah, you have like a file with the distances, the interatomic the positions rather of each molecule like in its own coordinate frame, so they're not related to one another at all.
okay, so is there anything you need to do to like basically cycling them all into the same frame before you input?
No, because this will be handled kind of automatically when you, for example, when you start using interatomic distances, they will all effectively be working in the same frame. So you don't have to do any kind of standardization beforehand.
Okay, gotcha. Makes sense. Thanks.
Okay, no problem. So yeah, there are also questions in the chat, but I will maybe answer those at the end. So if you have maybe like pressing questions throughout, maybe, yeah, I prefer a raised hand, please. Great, thanks. Okay, so we have all of these different modes or approaches to how we might be able to make predictions of chemical reactions. But in practice, we basically treat all of these options as hyperparameters because we don't necessarily know which approach would be best suited to different reactions, although you do need to specify in advance whether you have atom maps, yes or no. So I will talk about like how that affects the results. So in terms of the data sets, so this field is relatively new, so there are not such clear benchmarks, let's say, or such clear data sets that you should be using for benchmarking. So this is also something that I've spent some time working on, is collecting relevant data sets and thinking about what might constitute good benchmarks. So the most widely used data set is this GDB 722-TS. So this naming system is something that I came up with just to kind of standardize the data set. So you might see it appear under different names, but this is the data set that has been used the most because it's the largest. So it's around 12,000 reactions of mixed reaction class. And these are relatively small molecules because they're derived from this GDB7 database, which is basically molecules up to 7 heavy atoms. And again, yeah, you'll have separated reactants and products, and the target will be the barrier. And then another data set that is interesting, it's a little bit smaller, and it's a fixed reaction class. So they're all the same type of transformation. And these molecules are a little bit larger, so they have up to 50 heavy atoms. So this is already going to be quite a different data set from the first one, mostly because in the first case, you have mixed reaction classes, and in the second case, you have a single reaction class. I will show you how that affect things, and then of course the size is different as well. And then quite a different data set from the other two. This one is much smaller, so it's around 1,000, and also the type of reaction is very different. So this is one of the problems maybe in this domain, is that chemical reactions can actually mean a lot of different things. So in this case, for example, it's actually a single step in what would be like a multi-step cycle of several steps that take place in a catalytic reaction. And so the changes that will take place in this type of reaction are much more subtle than those that would take place, for example, in these cycloadditions. Because here, I'm not sure how well you can see, but to go from the reactant to the product, it's almost like a rotation of the groups on the right-hand side. And there are some bond changes, but it's nowhere near as severe as these ones, where you really kind of are like putting two molecules together. So these really pose different kinds of challenges. And I will also talk about how different models are better or worse suited to these different data sets. So I will also reiterate these different atom mapping modes because I will show results for all of them. So what I call true maps is that you used the mechanism, or you had like an expert chemist that deduced these atom maps. And it's also worth reiterating that you typically will not know this for new chemistry. So organic chemists working in the lab, they will find some new reaction, but they will not know, for example, what the transition state will look like. So yeah, I will kind of reiterate that this is not like a mode that will occur very frequently, but nevertheless, I will include it because you do have atom maps available for a lot of data sets. And then we have this reaction mapper mode, which is mapped using a reaction mapper. And we also have a none mode where the maps are removed entirely. And I will also use this reaction variation of Slatum as one of the baselines. And it's worth mentioning that this model can only run in this mode. So even if you have atom maps, this kind of fingerprint method will not be able to use them. So then to show you some results. So I'm looking at this first data set, which had the mixed reaction classes, and I have these three different modes, so the true mode, the reaction mapper mode, and the none mode. And it's worth mentioning that in this true mode, 3D React, so our model, is not the best model. Actually, this 2D based model, Chemprop, is. And this is because for this kind of data where you really have so many different types of chemical transformations, if you know the atom mapping or the mechanism, it's kind of all you need. So in the 3D React, we do also have it, but we also add a bunch of additional information in the form of geometry, which actually makes it a little bit more challenging to learn. And so Chemprop is still the best model. But when you move away from this kind of high quality atom mapping, you can see that 3D React becomes much more competitive. And in this regime where you have no atom maps, we're clearly the best model. And then this other model was this fingerprints also based on 3D geometries of features, but you can see that 3D React is a better model. And then looking at the cyclo-addition reactions, now you have a fixed reaction class. And so having atom mapping is also not particularly helpful because basically the mechanism is always the same. So in this case as well, you see that there's almost no difference in the performance, whether you have the maps or not. And in this case, also 3D React is always the best model. And now looking at this third data set, it's very clear that you need models based on 3D geometry because these 2D graph-based models, they really cannot capture these very subtle geometry changes that I mentioned. So reaction mapper is not present here because, as I mentioned, reaction mapper cannot map all types of chemistry, and so it cannot map this kind of chemistry. But nevertheless, again, you're not so dependent on this atom mapping information. It's just very clear that you do need 3D information. And actually this fingerprint-based method does do as well as 3D React here because the data set is very small. So we already consider it a success that our model can handle training on like 700 data points. Yes, there's a raised hand.
Yes, a small question. Seems like the range of errors varies a lot from one data set to another. And I was just wondering, what's the acceptable error for kind of, let's say you want to put this model in production, what's your acceptable error and which one will you put in production, for example?
Yeah, so in chemistry broadly, or in computational chemistry broadly, people like to see 1 kcal per mole. But for these types of targets, so the barrier, 1 kcal per mole is impossible even for like a computation. So usually a few kcal per mole, like 4 or 5, is quite good. So basically up to this range is fine. So all of these are fine. These ones are starting to become a little bit higher than what you would like. So this data set is very challenging, basically because of the huge range in the target value that is present in the data set. So these are much narrower, so it's kind of easier. But yeah, so I would say 4 or 5 is fine. So in this case, with the reaction mapper maps, it's fine, and all of these are fine. But
one quick follow-up question. The 3D React here, is it the vector one or the other one, the energy one?
Sorry, can you repeat the question?
The 3D React here, is it the vector one or the energy one?
Okay, so in most cases it's the vector one, but for this data set it's the energy one. And we put a discussion for this in the paper, but I don't have it in the slides. But it's because for this data set in particular, there is a linear correlation between the reaction energy and the barrier. So these two quantities that I showed you on the first slide. And if this is the case, then you can basically learn the reaction energy directly. And so this is much easier, and that's why you can use this energy mode. But for the others, it's always the vector mode. But we always run through both as a possible hyperparameter, but we think it makes sense that this one runs in the energy mode. Yeah. Okay. So that was for random splits. And what about for extrapolation? So in chemistry, maybe the most common extrapolation split is a scaffold split. So this basically means that you have a molecule and you remove basically side groups. So you keep everything that is a ring system and you just remove anything that's attached to the rings. And this constitutes your chemical scaffold. And so it's kind of assumed that in your data set, you will have other molecules with the same scaffold, but with different side chains, just because that's often how data sets are constructed, for example. And then the train test split will basically be that the most common scaffolds are present in train. And then other scaffolds that are less common are present in test. So this is quite challenging because you will see completely new scaffolds. And another approach is to do extrapolation based on molecule size. So then you would basically train on all of the smaller molecules and test on the larger ones. So this is also, yeah, relatively challenging to do. And you can do a very similar thing to size, which is a property-based split. So here you would basically just cut, if you wanted to do an 80-10-10, you would cut at 80% of your target, and those would all be trained, and then everything else, well, yeah, would be validation and test. And as I will show you, this actually turns out to be the most challenging split. So yeah, here I have the results for the 3 different splits, where orange is 3D React, blue is the 2D graph model, and green is the 3D structure-based fingerprints, and then the stars is the true maps, the dots is the reaction mapper, and the dashes is none, so the no maps. And the first thing to notice is that actually the difference between the mapping modes gets smaller. And aside from that, the difference between the models also gets smaller. So 3D React actually is competitive with Chemprop for all of the different modes already. And so for scaffold splits, the errors, so you can see already the errors are much larger. But so for scaffold and for size, this could maybe be expected for like extrapolation type splits, but the property-based splits really result in very large errors. So the property-based split is super, super challenging, which is maybe surprising because the size you would also expect to correlate with the property. But so the property-based splits, none of the models are okay. But then for the scaffold and the size-based splits, we would actually argue that 3D React actually seems to be a little bit less sensitive to extrapolation, just because in the interpolation case, Chemprop was beating 3D React in some cases, but now that's no longer the case. So we do think that it seems to be the 3D structure-based models do seem to be a little bit less sensitive to extrapolation. And then if we move to this, the next data set, so here again, but this was the case already for interpolation for this set, it doesn't actually matter if you use atom maps or not. And it's still the case that 3D React is the best model. And actually here also the errors are quite good for scaffold and size. So they're still under 5 kcal per mole, but the property-based splits do become more challenging. But so here we kind of maintain the same behavior that we saw previously. So the 3D React does seem to still be the best on this data set, even in extrapolation. And then moving to this third data set, we do still see the same behavior as before, where the 2D graph-based models are really struggling with this data set. But interestingly, for the property-based splits, all of the models are kind of almost equally bad. So property-based splits just seem to be super challenging for all of the models. But otherwise, again, same trend as before for the interpolation type splits, that the 2D based models are kind of inappropriate for this kind of data set. And then another kind of pressing question when you're actually training models on the 3D geometry is the quality of the geometry. So typically these data sets, because they are associated with usually DFT level barriers, the geometries of the reactants and products are also relaxed at DFT level. So this is something that you will not want to do in an out of sample scenario. So let's say you want to make predictions on some molecules for which you only have the SMILE strings. You want a cheap way to generate these geometries. So this can be done with this cheaper method that I mentioned, XTB. And the question was whether if you use these XTB geometries, can you still get good predictions on these higher level barriers? And the answer is yes. And for the first data set, you actually almost see no performance loss at all when you move to the cheaper geometries. And you can also see that this is not necessarily the case for these kind of fingerprint-based models. So this is very satisfying. But these GDB molecules, I mentioned, they are quite small. And basically the difference between the methods will become more pronounced with larger molecules. So that is indeed what we see. When we move to larger molecules, you do start to see a gap. Like it's harder to predict the DFT barriers with XTB geometries. But nevertheless, the performance loss is not drastic, and it would definitely be worth it for basically the computational time that you would save using these cheaper geometries. And then the most challenging case, the Proparg data set, again, you do see a performance loss, so it kind of makes sense that it gets worse and worse the bigger the molecules become. But you can also always see that 3D-React is much more stable than, for example, these fingerprint methods to changing the level of theory of the geometries. So we thought this was quite satisfying because it will lead to a much more practical model, basically. So it's good that we see this reduced sensitivity. And then in terms of kind of interpreting the model behavior, it's usually nice to kind of see that you have a correlation in the latent space with the target property. So here, for example, you see this very strongly with Chemprop, but you also see it with 3D-React, whereas you don't see it so much with the other baseline. And if you think about why this might be, so in this GDB data set, it's kind of subcategorized not into reaction classes, but into like which types of bonds break and form. So here, for example, you can see that in Chemprop, this chemical structure is very well represented. So it's clustering very clearly, specific types of bond breaking and forming, whereas this is not the case at all for 3D-React, which is not very surprising because it's not using chemical structure, it's using just like distances and angles to construct this latent representation. So it has a correlation with the target property, but not for the same reason as these kind of chemical-based models. And if we do some further analysis into these reaction classes, so usually it's nice to see that if, for example, you change the reaction class, that you still have stable performance. And so here you do indeed have pretty stable performance regardless of the reaction class. The only reaction class where you do see slightly higher errors and higher standard deviations is because these are actually reactions just involving a hydrogen-hydrogen bond. And our model is not trained with explicit hydrogen nodes. So we do this to save on compute time, but you can put the hydrogen nodes back in, and then you see that this kind of resolves this behavior. But nevertheless, this is very stable. Like it doesn't seem to matter. Like it has basically the same performance regardless of what kind of reactions you're looking at, which is nice. So to conclude, the prediction of reaction properties, particularly barriers, is really a booming field. And so it's quite interesting to think about whether you need chemistry or whether you need physics to make these predictions. And what I have shown is that it's really dependent on the data sets. And so the benefit of 3D-React is that it's able to incorporate both, depending on the available data, compared to the other available models, which basically either had the 3D geometry or had the chemical information. And we also show that it has a much reduced sensitivity to the geometry quality. And I still think these kinds of models are best suited to these datasets without the true maps. And in particular, they're very well suited to datasets with conformational diversity, like this Proparg dataset that I showed you. And I would welcome you to please try it out and tell me if you find some other interesting data sets or have some ideas. And finally, I would like to thank my co-authors, mostly Xenia, who is my shared first author. We really worked on this together, so it was really fun. And then Ruben and my supervisor, Clémence Commonbeuf. And this work was done in collaboration with the group of Andreas Krause at ETH Zurich, with Charlotte Bühner and Vignesh. And this was possible because I'm funded by the NCCR Catalysis, which basically encourages this kind of interdisciplinary collaboration. And then I also just have a PR slide because I will be finishing my PhD this year. So I'm interested in opportunities at the interface between AI and molecules. So please feel free to check my various social medias and get in touch if you might have something in mind. And I'm open to questions. Thanks.
Perfect. Thank you so much for the group presentation. There's a few questions in the chat. Maybe we can chat with
Yes.
those and
Yeah.
people will raise their hand afterward.
Yeah. Okay, sorry. So the signs, yeah, I should have explained that at the time. My bad. Okay, so back in the parity thing. So actually, if I go back to the slide where I had the molecules translating and rotating and stuff. Yeah, so the sign, it's basically this. It's like if I invert my molecule, which in this case is like a reflection in a mirror plane, the magnitude of the vector is the same, but the sign changes. So this is exactly what the sign means then in the, if I go to the spherical harmonic stuff. Yeah, like the odd even, the odd means exactly the sign flip, whereas the even would mean that the sign would not change. I hope that answers the first question. Okay, so then if I go to the next question, the attention. Yeah, so that's a good question about the, okay, I go back to that slide as well. Okay, so yeah, so it's a good question because you have noticed that equivariance is actually not preserved like end to end throughout the entire network. It's preserved for each molecular component. So you do lose information eventually, but the actual property, like the reaction barrier, is not an equivariant quantity. So you don't need the network to be end-to-end equivariant. You just want the individual molecular components to be equivariant just to basically contain all of the molecular symmetries. And so at this stage, these are equivariant representations. And then you permute them. And then you do some other operations that afterwards mean the network is not end-to-end equivariant. So yeah, it's a good catch. Yeah, I guess you could also try to do some kind of equivariant attention, but given that the whole network isn't end-to-end equivariant anyway, we thought it didn't matter too much, but yeah, thanks for the question. So the next one, I think you have mentioned it, but why don't we have the benchmark of model plus reaction mapper on the Proparg dataset? Yeah, so the Proparg dataset, it has quite freaky molecules. Don't remember when here. So for example, a reaction mapper is trained on molecules like these. So like with like carbon and hydrogen and oxygen and nitrogen. And it will never have seen molecules like this. Like these are like silicon molecules with like freaky groups. It will never have seen this stuff before. So reaction mapper will basically just complain and say, I have never seen these elements before. I have no idea what to do, which is kind of to be expected because it's not what it's trained on. So it's like, it's not possible to train reaction mapper on this kind of data. Okay. And then again, from Prudencio, using XTB geometries is mainly a way to see if larger low fidelity data can lead to more improvement. Okay, so it's actually not necessarily to have more data. It's actually more to think about what you would want to do in an out of sample scenario. So because these models are normally trained with the data that is published, which in this case, for example, all of this data is published at like an expensive level of theory. So like these molecules will have been optimized using DFT. So if you train a model with these geometries, you're also kind of if you train the model using these geometries, but then also test them using these geometries, you're also kind of assuming that you'll have like a DFT geometry if you wanted to actually do this for some unseen molecules. So we wanted to see what would happen if instead of using these already optimized structures, what would happen if, like, usually for some new molecule, you would actually just have the SMILE string. And then to go from the SMILE string to a geometry, the cheapest way to do that in a reliable way is with XTB. So we're using these kind of crappier geometries and we're seeing how that affects the model. But you can also indeed use those geometries like first for pre-training, and that can also help things. But that was not necessarily what we were trying to do here. We were trying to think of like a realistic out of sample model.
On that, do you think like, because like the size of the data set seems also quite small, so do you think it still makes sense to use semi-empirical method as a way to just explore the reaction space, get the transition state, get the the starting point, and just get the single energy computation at each of the state and get the data energy
Yes.
and predict that?
Yeah, I mean, it's true. It's not a bad idea because indeed, like the individual reactant product energies it's not so difficult to obtain. So if you could kind of go for a strategy where you try to generate as much data as possible. So you can generate these delta E's, and then you could try and learn some model that from these delta E's instead predicts the barriers. So it's a good idea. I haven't tried.
Thank you.
Okay. And yeah, there's a question in the chat. Did you consider transition 1x? So transition 1x is actually related to this first data set. So yeah, this is like an updated version of the original data set. So this one was published in 2022, but then there was one from the same authors like 1 or 2 years before. And that data set was actually the starting point for transition 1x. So transition 1x takes these molecules and it basically just runs molecular dynamics on them. But the barriers come from this data set because transition 1x doesn't compute barriers. It just gets, like, it runs molecular dynamics and it gets energies and forces on the atoms. So transition 1x is not exactly the data format that we want because we want like structures annotated with barriers. So that's why we don't use transition 1x. And then have you considered transition states determined from generative models? Yeah, so this was what I said on the first slide. So the transition state generation is kind of an alternative approach to the same problem. So it doesn't make any sense to both try to generate transition states and then, like, once you have the transition state structure, it's cheaper to do the single point to get the barrier than it is to also try and predict the barrier afterwards. So for me, they're kind of complementary approaches. So yeah, can you evaluate these structures? The way you would evaluate them is by running single points on them, and that's how you would get the barriers. Would there be issues you can foresee? Yeah, so well, the transition state generation is of course more difficult than the barrier prediction. So there's more issues in that, yeah, it's a more complicated model, but there's also advantages because, for example, yeah, maybe it's actually worth mentioning. On my first slide, you have the correct geometries. So if I go back to this diagram, so it's very difficult actually to get the correct transition state because you need to have the reactants and products in the exact local minima that would lead to this transition state. So when you do these kinds of computations, you do this what is called like a double-ended search, where you start from these structures and then you search for this one. But so these ones have to be correct already. Like the reactants and products cannot be any reactants and products. They have to be the ones that lead to the transition state. So this is kind of the hidden challenge with the direct barrier prediction, which is also why we try to just do like XCB structures to see how that would work out. And then, so then the advantage of the direct TS generation is that you don't have this problem because you're actually trying to sample the TS directly. But then the challenge you have with the TS generation is you have no idea if it's the right one. So it's kind of like the inverse problem. Like here, yeah, you're kind of assuming that you're predicting the barrier for the correct TS, but then when you do the TS generation, you're sampling it, but you don't know if it's the right one. So yeah, it's kind of a different approach. Okay, cool. So yeah, there were some raised hands. Ravi, maybe?
Yeah, hello. Thanks. Thank you for the presentation. I really enjoyed it. I just have one quick question. So, when you were, please correct me if I'm mistaken. I believe you were talking about chemical reactions and their relationship to the types of graphs, be it in the form of nodes and edges. So I'm just curious, how in these types of chemical reactions, do you have a general idea of how large the graphs are? Does it happen to have millions of thousands or millions of nodes and edges? Do you understand my question? Or?
Yeah. So when you construct the graphs, at least when you construct them with the 3D geometry, you usually do like a cutoff radius. So you say like, yeah, this is my central atom. I want to connect to everything up to, I don't know, 5 angstroms. So you can kind of tune the expense based on this cutoff radius. Normally, it's a good idea to restrict yourself to at least have like the up to 2 or 3 neighbors away. But so I guess, yeah, like for this, these are kind of like quite stereotypical molecules. So if in this case you were to account for 2 or 3 neighbors away, then each node would be connected to like up to 10 other nodes. So yeah, I mean, these message passing frameworks, they do blow up quite quickly. But so the actual molecules, in terms of how many nodes they have themselves, this is exactly correlated to the molecular size slide thing that I showed. So it's like up to 50 atoms, so 50 nodes. But then when you do the message passing, you are connected. Each of those nodes is also connected to like up to 10 others. But they're not millions of atoms, but it is expensive. Yeah.
Okay, I understand that. I mean, I just thought that like these types of reactions involve like thousands or millions of nodes.
No. I mean, if you were to do this with proteins, proteins are much bigger molecules, so you would have several hundreds of atoms, but you would never really have more than several hundreds of atoms for like physical systems. Yeah.
That's it. Thank you.
Okay. So then there was Daniel.
Yeah, hi. Thanks again for the great talk. I just wanted to clarify earlier, you're talking about like 5 kilocalories per mole is actually pretty good MAE for these problems. Is that just because you have multiple reactants and products, so you're kind of like summing the MAEs over each molecule, or is it something different?
Yeah, it's a little bit different. It actually has to do with the inherent error in the quantity that you're trying to predict. So if it's a single molecule and you just want to compute its energy, this is where this 1 kcal per mole idea comes from, because if the reference, so like the computations, let's say a DFT computation, can compute this quantity with an error against experiment, which would be like the real structure of less than 1 kcal per mole, you want your model to basically almost be able to approximate the inherent error in those like ground truth methods. So even things like DFT are actually quite bad at getting the barrier right. So that's why you're allowed a much larger error margin, because if the truth is the DFT label is also going to have an error margin compared to the truth, which is like the structure that is measured in an experiment. So like the error margins that you allow, they have to do with the inherent errors of these quantities. But you're right that to some extent, the reason why the error in this quantity is higher than the error in a single quantity is also because there's many moving parts. Yeah, that makes sense.
Got it. Thanks. And is there like a reason DFT's worse at computing these, or?
Yeah, that's like a rabbit hole. But
Okay.
yeah, it has to do with yeah, you know, in DFT you have like a functional, like you have a choice of functional. Might be going too far, but basically DFT is not an exact science. There's always a choice. And these choices are called functionals. And basically different functionals are more or less optimized for different tasks. And so you have some functionals which are very bad at the barrier task, and then you have other functionals which are kind of better. But yeah, the barrier is one of the most challenging quantities to compute in general, which is why it's such an interesting target for machine learning. Yeah.